Once I have this, I can represent both the solution. So U is going to be a summation. So let's use a Numerical method and a homogeneous boundary condition, at least a homogeneous essential boundary condition. So from I to n of let's say AI times Vi of x. Okay, and when solving the Poisson's equation, we need the integral of Aij being the integral from left to right of d phi dx times d phi j dx. And this integral now needs to be so previously when we have n elements, and if we have Dirichlet boundary conditions, so we only have n minus 1 basis functions. This matrix is n minus 1 by n minus 1. Now we have one more basis function per element, and the matrix is going to be 2n minus 1 by 2n minus 1. Right? And these are going to include so the matrices are going to be non-zero when the derivative of phi and derivative of phi j has non-zero overlap. So here what we need to do is for each element, we are going to have, there are three non-zero basis functions. Okay, so let's call it for each element I, we have three basis functions. Let me call it left I, middle I, and right I. Okay, so this left I is a function that goes like this, and the middle is a function that goes like this, and the right is a function goes like this. So like in our 2D case, we want to compute the contribution of this element in the matrix A. Okay, and the contribution is going to be a 3 by 3 matrix. So basically we are having a 3 by 3 matrix. Let me call this A superscript I. This is a 3 by 3 matrix, and the elements of this 3 by 3 matrix is going to be added on the big matrix A, with the row and column indices being this Li, Mi, and Ri. So we are going to take this 3 by 3 matrix and look at the big matrix and look at what is the column corresponding to Li, what is the column corresponding to Mi, what is the row corresponding to Ri, and also what is the column corresponding to Li, what is the column corresponding to Mi, what is the column corresponding to Ri. And this entry is going to go to here, this entry is going to be added to here, this entry is going to be added to here, and these correspondingly. So this 3 by 3 matrix ended up adding onto these 9 entries in the bigger matrix. Once we loop over all the elements and compute the contribution of each element into the big matrix, then we have formed the big matrix. Does it make sense? And this is because the integration can be split into a summation of integration over each element, right? So basically the matrix can be split into smaller into still big matrices, but with the contribution from each individual element. And this A superscript I is the contribution over the ith element. Okay, so on this matrix, these 4 entries corresponding to the left and right are going to be exactly the same as in the piecewise linear elements, because this corresponds to the so AI11 it's still going to be equal to 1 over hi. So this is because the derivative of this function is 1 over hi, right? Hi is the width of this interval, and we are squaring the derivative and integrating over a length of hi. So this is hi. Basically, we have the square of 1 over hi times hi. So this is hi. So we are going to fill it over here, 1 over hi, and this is also 1 over hi. We have minus 1 over hi here because we are multiplying a negative slope with a positive slope, and also the matrix is symmetric for Galerkin method. We also have minus 1 over hi here. So what's different is this for integrals. For the middle integral, let's make some space for this. AI22 is equal to the middle basis function. The middle basis function is let me see. So from integration over hi, the middle basis function square the derivative of the middle function, which is x over h, it's times 1 minus x over h, scaled by 4, because I want to make when x is equal to half of h, I want to make the value of the function equal to 1, and the derivative squared, right? Okay, so let's evaluate the derivative. The derivative of that is going to be a linear function. First of all, it has a constant term that is equal to 1 over h, and also a quadratic term that is 2x over h squared times 4 that thing squared. So what we have is an integration of a linear function squared. So let's actually plot the linear function. We have x goes from 0 to h. The linear function goes from 1 over h all the way to minus 1 over h. Okay, oops. And the square from 4 over h to minus 4 over h. The square of that function is going to go from, it goes to 0 here, and at the two ends, the square of that function goes from 16 over h squared. Right. So the area below that parabola is going to be 1/3 of the area of this whole rectangle. So the area is going to be 16 over h squared times h over 3. So that's what this is going to be. So it's 16 over 3h I. Okay, similarly you can do integration of this term and this term and this term and this term. So these are basically easier than this, because you need to just multiply a linear function with a constant function and integrate. And we can see that this type of integration gets a little bit more and more tedious as we go to more and more complex elements. So what do you think is an alternative of doing this kind of tedious integration? Symbolic is a good idea, especially nowadays if you go to Wolfram alpha, you can type a few things and it just pops out a result. That's a good alternative. What else? Gaussian quadrature. Gaussian quadrature is another great idea of integrating complex functions, because as you remember, like we have functions that may be complex, but it's very smooth and non-oscillatory, hopefully within an element. So with a few points, you can really integrate the function to numerical precision with Gaussian quadrature. And Gaussian quadrature also works on 2D and 3D on simple elements, right? So if your element is regularly shaped, you can, I mean, the worst case is you can split that elements into triangles in 2D and the tetrahedrals in 3D, and there are basically very good Gaussian quadrature rules for triangles and tetrahedrals. You can use them for 2D and 3D integrations. So that's what you can do for higher order finite element schemes. So you get a little bit more complications in assembling the matrices, but like with Gaussian quadrature, you can really write a very general code and do some really high order finite element methods.